just a brief reminder, a couple definitions. We said that A was congruent to B mod I, where I is some ideal and commutative ring if the difference of A and B was again an element of the ideal. We proved last time that this congruence mod I forms an equivalence class. One of the things that means, of course, is that everything in the ring fits into one of the equivalence relations. And what that means is that everything in the ring fits into one of the equivalence classes associated with this equivalence relation. In particular, the equivalence classes are I plus A, which is simply I plus A, where I is an I, that set of elements. And then if you want to think about the set of all such things, we say R mod I. So basically, what I'm trying to say here is that I plus A is an element of R mod I, okay? And so this thing right here, we will soon learn, is called the factor ring. So that's the factor ring, which by my terminology you might suspect is a ring. So one of our first orders of business is going to be to explain why R mod I, R divided by I, is in fact a ring, given that I is an ideal. Now you say a ring with respect to what? Well, this is going to be a ring with respect to this notion of addition and with respect to this notion of multiplication. Now whenever I define some operation on equivalence classes, it begs a question, right? How do I know that I can make those definitions independent of the type of representatives? Right? How do I know that? Well, and so the answer is, that's true. Let me show you. So here's a little theorem that will prove that that definition is worthwhile and logical. See here, so here's the theorem. If I plus A is equal to I plus A prime, and if I plus B is equal to I plus B prime, then I plus A plus B is equal to I plus A prime plus B prime, and also I plus A times I plus B is equal to, oh, sorry, it's not right. That begs the question. I say is that I plus AB is equal to I plus A prime B prime. You see, if I have these equalities, that proves that the definition I was just talking about over there is well defined, right? So the definition is independent of the choice of the representative. So this proof is not that hard. So how do we do it? So first of all, what do our, if we assume I plus A equals to I plus A prime, and I plus B equals to I plus B prime, what do these tell me?
A minus A prime is
Yeah. So consider A plus B, right, minus A prime plus B prime. What do we get? A minus A prime, right, plus B minus B prime. But A minus A prime is an element of I. B minus B prime, element of I. And the sum of things in an ideal, by definition, is what? In an ideal again. So this is an element of I. So therefore, I plus A plus B is equal to I plus A prime plus B prime. In other words, we can define addition by adding representatives without ambiguity. Right, the representative of I plus A is A. The representative of I plus A plus A, I plus A plus B is A plus B. So this shows that the definition is independent of our choice of representative for the coset. You can call I plus A a coset if you like. So it's a coset with respect to the additive group, the additive abelian group that we have in this ring we're working over. Now, let's see here. Now I need to do what? I need to look at the product. That proves this part. Right now I still need to prove that the I plus AB is equal to I plus A prime B prime. So I should what? I should consider AB minus A prime B prime, right? And as often is the case with some sort of product rule, you have to add 0. Right, so I add 0, I add AB prime minus AB prime. So I have AB, and then I'll add 0 in green. So plus AB prime minus AB prime. I can do that, that's adding 0. And then what do? I can factor out an A in the first thing, right? I have A times B, first and third, thank you. A minus B prime, and then plus B prime. B prime, A minus A prime. Now why would I do that? I do that because I know that what is in parentheses is an element of the ideal. This is an element of the ideal, right? But if you have a ring element times an ideal element, it's again, altogether, this is an element of the ideal, right? And this altogether is an element of the ideal because we have a ring element times an ideal element. Again, we have a sum of two things in the ideal. Therefore, this is also in the ideal. And so we have proved that I plus AB is equal to I plus A prime B prime. Which is nothing to sneeze at. Sorry. I don't know, maybe it is. Opinions vary. I'm just glad I'm not sneezing at you today. I would have been yesterday. Come on.
You haven't talked yet.
I know, right?
Person.
There's still time. Don't worry. At some point I'll laugh at you. No, it's just a hit open. I'll laugh. Oh no, I feel it coming down.
You jinxed him.
Good job, Sharon. So this definition, nobody over there, is reasonable, right? And we can soon prove that R mod I forms a ring. So let's do that here. How can we prove the theorem? I'll do it in black. Theorem. The factor ring, R mod I, forms a ring with addition and multiplication defined as above. All right? So, what does it take for us to form, to prove it's a ring? What do we need to do? Right, so we need to show addition is closed.
Multiplication and subtraction.
Yeah, we need addition, we need multiplication. There's going to be a 0 in there, right? So, first of all, let's see here, proof. Basically, the proof is just to steal from the ring itself, right? Steal from R. So, in particular, I know I plus A plus I plus B. What's that equal to? Well, that's equal to, by definition, I plus A plus B, right? But that is equal to I plus B plus A, right? Because these are equal, which is equal to I plus B plus I plus A. So the addition is commutative. So the addition in the factor ring is commutative because the addition in the ordinary ring is commutative. The factor ring has a 0 also, right? What's 0? So observe that I plus 0 plus I plus A is equal to I plus A as what? Well, maybe I should put an A here first. Let me put an A there and a 0 here, just to make it more natural. So A minus 0 equals to A, right? Excuse me. A minus 0 is equal to A. Oh, I'm still not getting to the point of it. I mean, I guess I could just say A plus 0. I mean, there's a couple different ways I'm thinking about proving this. So how do I show this plus that gives me that again because A plus 0 is A, right? So that shows you that I plus 0 is behaving as what?
0.
The 0, right? So hence I plus 0 basically is 0 for R mod I, if you want a notation for it. Every so often I find this notation is convenient. This is the 0 for the factor ring. Now, for our purposes, it's also convenient to allow ourselves a slight relaxation in the notation, right? So instead of writing I plus 0, often we just write what? Our convention is to allow ourselves to also just write I. So I plus 0, or I, plays the role of 0. And the other multiplicative properties are proved in a similar fashion, right? So like, let's see here, well, actually, let me not do those. Those would all make good test questions. But, you know, you can keep doing these, like prove the distributive property, right? So exercise, show that I plus A times I plus B, parentheses, plus I plus C, parentheses, is equal to what? The distributive property says we should have what? We should have I plus A times I plus B, right? Plus I plus A times I plus C. That would be the distributive property of multiplication in the factoring. So, oh fine, I'll show it and drift you to it. So this is I plus A times I plus B plus C, right? And what's that equal to? Well, that's equal to I plus, by the definition of the product, that's A times what? B plus C. Now you can use the, it always comes back to this. You apply the definition in the factoring of the multiplication or addition, and then you use the corresponding property in the ring to prove that's the real, you know, how do I know I can distribute that? Well, A plus BC is happening in the ring R, which we know has the distributive property, right? R a ring. And then you undo it. So this is equal to I plus AB plus I plus AC, which is then equal to I plus A times I plus B plus I plus A times I plus C. I see I've written it anyway. So there you go. There's the distributive property in more detail, perhaps on the viewing screen. We don't know. It's good? All right. Sorry, it's fun to tease babies right now. because today's the day. But now, one other thing, if 1 is not an element of I, then we have this, right? I plus A times I plus 1 is equal to what? I plus A times 1, right, which is equal to I plus A. So I plus 1 plays the role of what? The multiplicative identity. But you see, if the number 1 happened to be in your ideal, what happens?
That's like 0.
Right, the factor ring, that essentially makes 1 equal to 0, right? But the factor ring doesn't have a 1 in it, right? So R mod I is not a commutative ring with identity if 1 is contained in the ideal by which we're quotienting. But on the other hand, if 1 is an element, what happens if 1 is an element of I? I is equal to what? We proved this the other day, right? It's the entire ring. So in this rather annoying case, we simply have R mod I is equal to R mod R, which, by the way, is essentially just 0. Yeah.
So if we did something like I plus A times I plus 0, would that just equal I then?
I plus A times,
I plus, like, I, just I. So it's I plus 0. So you're following that same rule right there? It would just be
I'm sorry, I'm not following you. I did what? So just
Like,
say
what
again.
would you like get if you did I plus A just times I?
I don't know. I'm talking about adding and multiplying cosets right now.
But like, so if it, like 0, it's not possible to just add 0 part of it? Like I was saying in the form of like that over there, like how you did I plus 1. Instead of I plus 1, just replacing it with I plus 0.
Oh, that's I again. We proved that over here.
Yeah.
You're talking about this again?
Oh, okay, sorry. I missed that.
That's okay.
Sorry.
No problem.
even in the case of like multiplication though?
What do you mean? Addition and multiplication are different in a ring. I mean, we do assume that everything has an additive inverse. But generically speaking, we don't make such an assumption with multiplication.
Okay.
Even in the ring with the strongest form of units, like the most possible units, even there, we do not assume that everything has a multiplicative inverse. 0 never has a multiplicative inverse, even in a field.
Okay.
So, it can't. I think that's one of your homework problems. Give or take. Anyway. Well, I guess that's debatable since I have freed you guys. All right, so now that we know the factor ring is a factor ring, I mean, it's a ring. Ultimately, our goal is to understand factoring in the factoring. Okay. Exactly. We may or may not get there today, but we've got time. Oh man, tell me I didn't bring my juice.
I want to share with this.
Where's my juice? Did I not bring the juice? Have my juice. Lost?
That's a song.
Oh. It's okay.
Hey, by the way, what is today?
You said you just study this board with.
All right, so this just brings us to section 12.2, which is on prime and maximal ideals. So we're going to go over some theorems today, which are really easy to understand and really easy to prove. And if you can remember them all at once, you can do a lot with them. The trouble is to get these things to stick in your head. So this theorem gives us the characterization of prime ideals. So, listen, I'm not going to write it again, but it should be understood that R is a commutative ring with identity, and that I is an ideal in everything we do here, okay? So here we go. I is prime ideal. The prime ideal if and only if R mod I has no zero divisors. All right. So what's a zero divisor, by the way? Do you guys remember?
Non-product of non-zero elements is 0.
Exactly. AB not equal to 0. We got
Done, PJ.
AB is equal to 0. That's good. All right. Not sure what's happening here. I'm going to go on. So proof.
My name is PJ.
Your name's PJ. Is that like peanut butter and jelly?
PB.
I'll explain another time. Out on video.
So when I was in community college, there was this guy. And he was always called by this abbreviation, but the professor would refuse to explain what the abbreviation meant. He said that before we got there, there were no women in the program, and certain things could be said that could no longer be said in the presence of mixed company. And so he categorically refused to explain the meaning of this abbreviation, which I'm not going to share with you in the fear that it actually means something to somebody. I have no idea to this day what it means, nor do I want to, but I just find it amusing. Anyway, so for implication, I prime, assume I is prime, ideal, okay? What should we do? Let A plus I times B plus I equal to I. If you like, I plus 0. The point is, I have a product of two things in the factor ring, right? Product of two cosets is 0. I need to show what? It has to be 0, right? Now, and what that really means is I have to show what? Our goal is to show either A is an element of I or B is an element of I, or both. I mean, so I could just say A is an element of I or B is an element of I. But what we have then, what this gives us is what? This gives us I. Oh, I'm sorry. I wrote it backwards. My apologies. I'm trying to do this. I plus A. There is a distinction, right? I'm trying to work with these kinds of cosets, I plus A, I plus B. I wrote A plus I. It's every so often I slip up and do that. I'm sorry about that. So I plus AB. I mean, I don't want to double the amount of notation you need to understand. Right? It's just with I plus A. Okay, so I plus AB. What's that mean? This? Exactly. So AB is an element of I. But remember we proved last time about prime ideals. If the product AB is an element of a prime ideal, A is an element of I, or B is an element of I. But you know what? Right? That's exactly what we need to do. So I guess I'll just go one more step, just to be super clear. That implies that I plus A is equal to I, or I plus A is A plus B is equal to I. In either case, we see there are no zero divisors. Right? So prime implies no zero divisors. Thanks, Sharon.
Come on, share.
Sharon.
Whole world's gonna know
Oh,
who you are.
Suppose R mod I has no zero divisors. Now we need to show that I is prime, right? So let A be an element of I, right? What is our goal? our goal is to show what either A is an element of I or B is an element of I. That would prove that I is prime by our second characterization of prime ideal from last class. But if AB is an element of I, that means that what? I plus AB is equal to I plus what? I plus A times I plus B. Oh, excuse me. Still not quite to the point. This is what though, main style? Yeah, this is I, that's the assumption, right? So I can say this is I, right? But again, no zero divisors, right? Therefore what? I plus A is equal to I, or I plus B is equal to I. But what does that say about A and B? Right, so this would say that A is an element of I, and this would say that B is an element of I. Hence, I is prime ideal. Everybody got it? That brings us to our next theorem, which is the characterization of maximal ideals. Theorem: I is maximal ideal if and only if what? What is this, Jerome?
What?
What is it?
Aaron was just telling me a joke about maximals the other day. I was trying
Our I is a field.
You were good.
Okay, I know if I run out of time at the end, Sharon's gonna give me 10 more minutes.
I did not do that. Daniel.
What is a field? Right back. Field is if A is not equal to 0 and A is an element of F, then what?
A has an inverse or C.
Right, there exists A inverse such that A inverse is equal to the number 1. Okay. In other words, every non-zero element of the field is a unit. Is a fast way to say it. Okay, so again, proof. What direction? Suppose I is maximal. Right, what does that mean? That means that if J is an ideal which contains I, right, that implies that either J is equal to I or J is equal to the whole ring. So a maximal ideal is one which is not properly contained in another larger ideal, unless the whole ideal is that ideal is the whole ring. So we seek to show that the factor ring, R mod I, is a field, right? So what do I need to do? I need to suppose that A is not an element of I, right?
And show that as an inverse. then.
Exactly, yeah, exactly. I plus A is not equal to I, right? We want to find a multiplicative inverse for this. Now, the simple way to do that is, it's essentially the trick we went over last time. So we're going to construct an ideal, construct J, by adjoining A to I. I mean, basically, that's just J is equal to what? It's going to be IR plus AS, such that I is an element of I, and you know, R and S are elements of the ring. You can prove that that is an ideal, right? But it's an ideal which certainly contains I, right? This contains I, because you can just set S equal to 0, and you get all the elements of I. So it definitely contains the ideal I, right? Consequently, by maximality, J has to be the whole ring, right? Thus, 1 is an element of J, you know, which is equal to R again. And that implies what? 1 is equal to IR plus AS for some ring elements R and S. Now, of course, this is what? I mean, IR is an element of what? This is an element of I, right? So what that means is that 1 minus AS is equal to, is an element of I, right? Which tells us that I plus 1 is equal to I plus AS. By the definition of the cosets. Hey, but the product says that I plus AS is equal to what? I plus A times I plus S. And remember, I showed back in the proof that R mod I forms a ring, I showed you that if you have the coset which has representative 1, that behaves as the multiplicative identity. So what I'm trying to tell you is this really is the number 1 in the factor ring. Okay, if you want to give it a more cumbersome name. So here you go. I have the product of I plus A and I plus S is equal to 1. So therefore, I plus A, if you want to use the other notation, inverse is equal to I plus S. Or if you want, some people will even feel free to say this, 1 over I plus A is equal to I plus S, but I don't usually use that notation here because it gives you guys a false sense of what you're doing. So let me just erase that before some of you get a bad idea. Just notation. Okay, there you go, that's the forward direction. Now we have to do what?
Stop.
This way. So what should we do? Assume R mod I is real. We wish to show that I is maximal ideal, right? pretty goofy today. Excuse me. Um, So again, consider A not an element of I, right? The reason I want to do that is I want to show that if you have an ideal which has a point outside of I, what does that ideal have to be? The ring itself, yeah. So let's suppose J is an ideal containing I, and it contains a point outside of I. Right? But I plus A is an element of our mod I, right? The factor ring, it doesn't just concern the ideal, it concerns all the elements of the rings, right? You take representatives from the whole ring, you know, and you're setting I to 0 in some sense, right? But I plus A is an element of the factor ring, and what else do we know? So that implies what? Right, so I plus, let's say, S is an element of R mod I, and I plus A times I plus S is equal to I plus 1, right? But I plus A times I plus S, now this is an element of the ring J, right? Because J contains A, right? So if you think about it, anything in there has to be an element of J. I should really say this is a subset of J. You know, this ideal J, it contains everything in there, right? But and then so this has to be a subset of J, right? But that means that I plus 1 is a subset of J, which implies that 1 is an element of J. Which means that J is the ring again, right? I hope you're noticing a theme here. If you want to prove maximality of an ideal, your goal is to show that 1 is in there pretty much. Once you've got 1, then you know it's the whole ring, right? So to show that I is maximal, you pick a point outside I, right, inside the larger ideal which contains I, and then your goal is just to show that that larger ideal necessarily then contains 1, and hence the ring. That seems to be the argument we keep going back to. So, okay, anyway, so thus J is equal to I, hence I maximal. If you don't like the argument I just gave, if you'd rather think in terms of points and elements and so forth, you can look at my notes, they're a little bit different. Look at Stillwell, he's a little bit different. If you don't like the subset argument I just used, you don't have to. It's fine. All right. So that brings us to a new definition. It's not really that new. Just give a label on things we've already seen. A particular flavor variety, let's say. I'm going to put the definition here. Definition. A commutative ring. With identity. Oh, a commutative ring with no zero divisors, rather. Is an integral domain. call a commutative ring with no zero divisors an integral domain? Let's see here. How about an example? How about r equals to the integers? You add two integers, you get an integer again, right? Multiply two integers. You get an integer again, right? There are no zero divisors. No way you can get the product of two integers being zero and have neither of those integers being zero, right? So the integers are your quintessential integral domain. And that's why it's called an integral domain, in reference to the integers. Okay? Now, one of the fundamental properties of an integral domain, theorem, an integral domain has cancellation. Little property. In particular, if we have AB is equal to AC and A is not equal to 0, that implies that B is equal to C. One of the fundamental mistakes of undergraduate mathematics in the abstract context is to assume the cancellation property where you have no right to. It's a fundamental mistake people make in lots of courses. Linear algebra, abstract algebra, that's most of it. I don't know. Oh, abstract algebra 2? No. Now here's why this is working here, so proof. So assume that A, B, C are elements of D, an integral domain. All right. And A is not equal to 0. Also, assume AB is equal to AC. All right. So if AB is equal to AC, that implies what? That implies AB minus AC is equal to 0. But what does that imply?
Do we have factoring in this?
It's a ring.
Oh.
So yeah, in a ring we have the distributive property, which basically is factoring
So
in reverse.
A times B minus C.
Yeah, A times B minus C equal to 0. And then we're pretty much done, right? But A is not equal to 0 is assumed. So since there are no zero divisors, that implies B minus C is equal to 0, which of course implies B is equal to C. Once you have the definitions right, things are beautiful and they work together like nicely. It's really satisfying as part of math because we're not the ones who constructed it. We are reaping the benefits of good definitions that have uncovered the true structure, you know. And, I know that's what my feeling was that when I first studied these things. It's like, man, abstract algebra is easy. Ah, it's so easy. You see, well, you could disagree, but I mean, people are entitled to their opinions, right? But you know, after having the experience of then trying to make my own definitions for other things, I started to appreciate this hidden difficulty. You see, most of the difficulty actually is finding the right definition to encapsulate the idea you're trying to communicate in abstract math. So once you find that right definition, everything just tends to line into place. But before you do, it's a mess. So anyway, lemma. A finite integral domain is a field. here, proof here is really simple. Let A be non-zero, and then just start looking at a list of powers of A. All right? So, proof. So, oh, I need to come up with a name. Let's call this domain, usually use D for domain, integral domain. So suppose A an element of D and A is not equal to 0, all right? Where the number of things in D is less than infinity, right? If you want me to get all highfalutin, the cardinality of D, it's fine. All right. Anyway, I think number D works good. Okay, so consider A squared, A cubed, A to the 4th, dot, 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 dot. This cannot be a genuinely infinite list because it's going, where is it? It's inside D, which is finite, right? You can't multiply things in an integral domain and get outside the domain. By its nature, it's closed under multiplication and hence powers of a single element. So consequently, that implies that there has to be some m and n such that a to the, m plus n is equal to a to the n. In other words, there has to be some place where it comes back and loops back to where it was before. All right? But if that happens, what does that say for m and n in the natural numbers? What does that say? That says that a to the m times a to the n is equal to a to the n. And let me just rewrite this a little bit more suspiciously. 1 times a to the n. But we are what? We are in an integral domain, which means we have the cancellation property. So I can cancel, and oh, do we know that a to the n is not equal to 0?
Yes.
Yeah, because a is not 0. It's easy to show if a to the n were 0, that would give you a 0 divisor with respect to a. If there are no 0 divisors, it's an integral domain. Hence what? A to the m is equal to 1. The role of n and m are flipped in the book and in my notes. Don't be bothered by that. They're just labels for the idea. Hence what? A times a to the m minus 1 is equal to 1. So therefore a inverse is equal to a to the m minus 1. Right? And that's it. Because a was arbitrary. So we just showed that an arbitrary non-zero element of the integral domain, the finite integral domain, has a multiplicative inverse. Consequently, a finite integral domain is a field. And you already know there's no hope of extending this to the infinite case, right? By our example, the integers, here's an infinite integral domain, which is not a field, right? You notice that 2 is an element of Z, but 2 inverse has to be 1/2, because we know rational numbers, and that has to fit with this, right? And that is not an element of Z, so it's not closed under inverses. There is no multiplicative. In fact, there's only 2 things with multiplicative inverses in the integers, right? 1 and minus 1. Those are the units. That's it. Okay. That wasn't too bad, was it? So let me just say some words. Every field is an integral domain, right? In a field, you can't have 0 divisors. That's easy to prove. However, not every integral domain is a field, right? Unless, of course, we make the provision that the integral domain is finite, in which case it's automatically a field. Likewise, we proved that every maximal ideal was prime last time, right? Remember we proved a maximal ideal was necessarily prime. However, not every prime ideal is maximal. But I had an awful hard time trying to come up with an example of that, didn't I? I started looking for a prime ideal which was not maximal. And I couldn't find it. And you know why I couldn't find it? Here's why. Theorem. Theorem. A prime ideal in the ring of integers of the imaginary quadratic field q adjoining square root of d. Again, d is less than 0, d square free. That's what makes it a imaginary quadratic field, right? So a prime ideal in the ring of integers over an imaginary quadratic field is a maximal ideal. And just to seal the deal here, to complete the thought, hence prime if and only if maximal in this context. Because we proved maximal implies prime last time. Now this theorem is this theorem draws together ideas, all the theorems we've done today, and a few things we've done in the past. The proof of this theorem is really, it's intricate, but it's simple. So here we go. Proof. All right. Almost dead ready marker. Whoa, did not hold up.
No, it landed on the chair.
Cool. It's like propped between my coat and... All right, anyway, proof. So let R be the ring of integers. Let R be integers of Q square root of D, D less than 0, square free. Also, suppose I, a subset of R, is a prime ideal. Observe, by the lattice property, of I, that R mod I is finite. I'll draw a picture to expand on this thought, but let's not get stuck on this. Accept with me for a second, for the sake of completing the proof, that R mod I is finite. Okay, we can argue it with a picture shortly. But what? Recall that R mod I has what? Has no zero divisors. Why? Since I is prime. Remember that theorem? A prime ideal has no zero divisors. It was like so 40 minutes ago. Right there. Thus, R mod I is a finite integral domain. But you remember like 5 minutes ago, a finite integral domain is what? Yeah. But then what? Remember, we also know, yeah, our mod I is field if and only if I is maximal. That was so like 30 minutes ago. This guy. We proved that even today. You already forgot, but we proved it. I know. These things don't stick in your head. They're just words. It takes time for you to internalize them. Working through these proofs by yourself without copying them would probably be a good step in the direction of remembering them. At least that's what I find. I have to be able to derive things to really have ownership of them mentally. Anyway, so R mod I is a field if and only if I is maximal. Oh, but then we proved that prime implies maximal. I love this proof. I mean, this one, it's got everything. Okay, so why does the lattice property give you that R mod I is finite? So what does the lattice property say? It says that we can picture I basically something like this. Right? And so I'm thinking of this being like 0, this being, say, alpha up at beta, let's say, and this being alpha. Remember, the lattice property said that I was equal to m alpha plus n beta for m and n integers, right? So this first cell you could think of as being sort of a fundamental domain. I think the 4 corners of this cell give you like I plus 0. I think I can prove this. I plus 0 is equal to I plus alpha is equal to I plus beta is equal to I plus alpha plus beta, right? So that these 4 corners are identified because, of course, alpha minus 0, beta minus 0, alpha plus beta minus 0, these are all elements of I. So yes, those 4 corners are in fact giving you this. Those are different representatives for the coset of 0, right? And then if you start thinking about, this is the larger picture, right? The actual ring of quadratic integers is finer than this. So the quadratic integers are something like, they're fitting inside here somehow or another, you know? I can't draw them with anything, but you get the idea. I can't draw them with anything, but the point is there's, oh well, I tried. It turned out badly, but you get the idea. If I could draw with anything today for this, there's, you know, a finite number of points inside there, inside the quadratic integers, right? And let's just focus on a particular one, like this one. That is the same as this point, is the same as this point, is the same as this point, is the same as this point. And because you can add an element of I, namely alpha, it's the same as this point, and 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 this point. And this continues, and on and so forth and so forth and so forth, forever and ever and ever. And so if you look at a single cell, that single cell, because you can add integer multiples of alpha and beta, in other words, an I element, to get to any other point in the plane, to count the number of equivalence classes, to count the number of cosets in the factor ring, it suffices to look at one fundamental cell. I think it's the number of distinct dots I think, I don't know, the edges are what I'm not 100% about, but definitely every interior dot gets you a representative. I'm not sure about how many you get from the edges without thinking more about it, but that's not really important. The details of the counting aren't so important. The point is it's finite. So R mod I is finite. It's a finite, yeah.
If it's made from rational numbers,
But this is in the ring of integers of this. And so we know from section 10.4 that that's either integer or half integers, like we saw with the Eisenstadt. So it's a discrete grid. It's not. Yeah, if this were rational. Oh, no. Yeah. But studying lattices in the plane is a very interesting topic, and there's a lot more to say about that.
So that's made of integers that are of.
Yeah, the integers of the quadratic field, right? So for example, if we're talking about d equals -1, you know, what are the integers of q adjoining the square root of I? Square root of -1, or in other words, q adjoining I. Those were the Gaussian integers, right? It was a plus bi. So in that case, it's just a straight rectangular grid, right? Or if we're talking about v adjoining the integers of q adjoining the square root of -3, there we learned it was the Eisenstein integers. So we also have like the half integer sums of 1 and the square root of -3. That was it. We proved that was all that was out there in terms of integers of an imaginary quadratic field. That was the sum total of it. Real quadratic fields, I don't know anything about. Seems like a good point to stop here today for the material. I'm going to yet again try to show you a video.
Yes. Are we gonna get them back tomorrow?
No.
What?
No.
Really?
Why?
She keeps falling asleep. She'll never finish.
We turned him in like a month ago.
Really?
Yeah. Where were you?
I tried so hard. You fell asleep like 3 times before I was able to actually sleep over there.
You want to see the video again and be scared?
What?
It's like, Chris, how did you end up finishing it? How many did you finish the mission?
9.
9.
Not including the reading.
So including you guys?
Does he include
What?
the
I
reading?
think I begged your question twice.
Does he include the
Mine.
reading as a question?
I hope so.
I think you did. It is a picture, it's a number.
Make sure that you have lambda
What's the video of?
bar.
Somebody
That's
teaching?
that is also the conjugate of that. And when you multiply this with the conjugate,
Here we go.
it goes to 1. So lambda times lambda bar.
Discussing here is a three-way correspondence between 3 different, a priori different subjects. One is the geometric line-less correspondence. Another is 4-dimensional super young males. And the third one is a 2-dimensional conformal field theory. Initially, I guess the first of these links was this one between the geometric line-less and 2-dimensional conformal field theory, and I'm going to talk a little bit about it at the beginning of my talk. And later on, in the work of Kapustin and Whitman and others, it was realized that also there is a deep connection between the geometric line-less correspondence and S-duality in 4-dimensional super young males. And more recently, Alday, Gayota, Tachikawa, and others have discovered beautiful connections also between 4-dimensional super young males and 2-dimensional conformal field theories, and some of that we have already heard here last week, and we'll hear more about this in the remaining days of this conference. So, but now I would like to add one more topic to this, so it will actually be a square instead of a triangle, and that's quantum integrable systems.
This is not the one.
Is the top word for the tall professors?
next slide's down.
What?
Like this later, the next slide down, so you don't have to erase.
That wasn't bad. What is
No, was it?
That's like almost like prejudice against like heights.
Come on.
Sharon, you have a filter. Oh my.
Best of my math jokes.
Come on. Stupid thing. There you go. You guys need something more relaxing. Anyway, I think I proved that. I think I proved to you that he's a legitimate mathematician. Yeah. His name, the guy we were just watching, is Russian. His name is.
Sure.
What was he saying when he said SYM?
Super Yang Mills.
Yang Mills, what's that?
Yeah, he's giving talks about something called the Langlands program, which proposes, fantastic links between things which were previously understood. It's an
Question.
ongoing thing.
I think there's several reasons. The problem is multidimensional. Why do so many people hate mathematics? Very good question. I think there's several reasons. The problem is multidimensional, no pun intended. Imagine that you had to take an art class in which you were taught only how to paint a fence or a wall, but were never shown the paintings of the great masters. Would that make you an art lover? Years later, you will talk to your friends and say, oh my gosh, I hated art at school. I was so bad at it. What you would really be saying is, I was bad at painting the fence. And likewise with mathematics, people often say, oh, I was so bad at math, I hate math. But what they're really saying is, I was bad at painting the fence. So how do we make people realize that mathematics is this incredible archipelago of knowledge? If you want kids to understand and appreciate the beauty and power of mathematics, we have to connect it to our daily lives. Let me give you an example. Say you go on Amazon to buy a book, and you are immediately presented with various recommendations. How does Amazon come up with these recommendations? Well, there are sophisticated algorithms at play which analyze your past choices, which correlate you with other users who are deemed to have similar preferences. Then all this data is processed and you're presented with these choices. Now, I'm not saying that this is necessarily a good thing, but I think at the very least, we have to be aware of this. We have to be aware of these algorithms invading our lives, and those algorithms are based on mathematics.
You and I live in houses and we appreciate the houses we live in. It doesn't mean we need to know how to lay bricks.
That's right.
So why, just because mathematics is underlying some of our technologies in our life, why does that mean we have to understand it or even appreciate it?
That's a very good point. And likewise, people say, well, we fly airplanes without necessarily understanding the physics of flight. But there is a difference. First of all, mathematics is part of our culture, just like literature and art. And you have to have a fulfilling life, we have to be aware of this. But also, because mathematics is becoming so important in our lives, there is a lot of opportunity for misuse of mathematics and for manipulating us by using highly sophisticated mathematics. There are many examples of that. Global economic crisis was to a large extent caused by misuse of mathematical models, which one could argue often were used by executives of financial firms who did not fully understand them. What if we lived in a world in which a Wall Street executive would not say, oh, I don't get this stuff, but as long as it works, it's fine. What if, in fact, that person would say, okay, tell me more about it. I would like to understand how this model works. There's this great quote, a great German mathematician, Georg Cantor, said, the essence of mathematics lies in its freedom. But I would augment this with the following, where there is no mathematics, there is no freedom. So mathematics is essential to our freedom, to the functioning of our democracy. That's why it's not just about finding out how some things work, which you don't need to know about because, who cares, as long as they work. I think that our ignorance can be misused by the powers that be. And for us to be, citizens in this new and brave new world, we have to be more aware of mathematics. We have to know and appreciate its power to do good, but also to do well.
The art world tells us we should appreciate art more. An English professor will say we need our language skills improved. Computer scientists will say we need to understand code. The mathematicians are telling us we should appreciate maths, or some of them are. We've only got these finite brains and only so many hours on the planet. Why do you rank mathematics above the others? I know you're a bit biased.
Well, first of all, I'm a mathematician, right? But also, I would say art, for example. Let's take art. So the situation with, of course, people don't go to art museums. We know that not everyone goes to art. Not everyone pays attention. But at least people know that there exist museums. If you say the word art, they don't think about painter and fence, but they think about Van Gogh and Picasso and Leonardo da Vinci. So they know that at least if they have an interest, they know where to go.
Am I allowed to finish, Chair?
Or they can go online.
Sure, you're gonna answer
In the
why
case of
say no.
mathematics, they're not even
All right.
aware of the
Raise your hand.
aware of the existence of mathematics. They're artists. Art.
I'm gonna use a filter.
You just filter.
Emotions, and it speaks about the world and about ourselves. But in a way, one can survive without it. But one cannot survive without mathematics. Everything is based on mathematics. It is the language of nature.
Well, let's apportion some blame. Let's blame someone then. It sounds to me like you're blaming high school teachers. You were saying, no, back in our school days, they're making us paint fences instead of showing us Picasso.
Well, if I really were to assign a blame, I would assign the blame to myself and my colleagues, professional mathematicians. We don't do nearly enough.
Anyway, I'll show you more about this guy later. Just to let you know, I'll send you a link to this so you can finish watching it. You guys got stuff to do. But his name is Edward Frankel. He grew up in Soviet Russia. So see, maybe about 1988 or so, he immigrated to the U.S. His life story is very, very interesting. He's one of the best mathematicians that's currently alive. He's very, very interesting. His opinions on things. I'm going to probably share with you another video where he talks about appreciation of math, basically. And I think he gives you one of the strongest arguments for appreciating just how math is part of the general revelation of God. He's not a Christian. He's not even, he's ethnically, I think he's Jewish, but I don't believe he's a practicing, I don't think he's religiously Jewish. But if you listen to him, the way he understands what mathematics is and the role it plays, you get a really strong example of why I would argue that mathematics is part of the general revelation of God. It's part of what speaks to his existence and part of what gives us this understanding that there's something undeniably beyond this physical realm. I think it's hard to see that with arithmetic and things, but when you start studying abstract algebra and the more modern mathematics, you start to come into contact with this. But anyway, I shut up.